Yeah. Okay. Yeah. Let's go. Just before starting, feel free to ask any question during the presentation. Don't hesitate to interrupt if you have any problem or interrogation. Thanks. So hello again. I'm Jean-Marie Vient, actually PhD student in the EMT and the European Institute of the Sea in Brest. This presentation will speak about part of my PhD work. First, concerning the interpolating of sea surface oceanic data, and a second part concerning the provision of the same kind of data with neural network methods, mainly based on end-to-end architecture. Here we got three pictures, three snapshots. Those three snapshots come from satellite observation, satellite data. As you probably know, satellite data are commonly used in oceanic and physics analysis. There are many advantages, mainly considering the accessibility of the data. We got a lot of products, a lot of way to get it, but also the precision of the new sensor. For instance, the Sentinel-6, which will be arrived with a brand new sensor, which have great upgrade concerning the last one. But also, and this is the principal advantages of working with satellite images, is the amount of available products. We got a lot of data, like I think of the MODIS data, which provide almost 20 years of data, which is maybe considered as a treasure for physical and oceanologists for the analysis. But those observations from satellites have a principal big problem, is that, as you can see on those two images, we are in the case with a great lake of data. Satellite data are all irregularly sampled. Sometimes you get a remote calibration issue, which may provoke unusable data for the analysis. As you can see here, we got a temporal series, for instance, with only a dozen of measurements, contrary to the true signal symbolized by the green time series. So I think a great interest to work on the way to interpolating those data and to give to analysts in oceanologists the best product for using in case of, again, analysis in physics or oceanology. This PhD work focus mainly on the sea surface sediment concentration. Sea sediment surface concentration is related to the estimation of the turbidity. Turbidity is a key value in the oceanic processes analysis. First, they are highly linked to the continental and fluvial sediment apport, and it's well associated to the biology. For example, concerning the amount of light and the visibility under the sea surface, which may consider the photosynthesis and the link to the phytoplankton. But also in sediment, we have a lot of nutrients, like silicate, phosphate, nitrate, also influence the biology. All those components make the SSE very, very important in terms of turbidity, visibility, and also for the biology impact. But concerning the SSE, we got not so related work, and we suffer for the same satellite lake of satellite observation data. So we focus on interpolation benchmark. So we just ask the question, what is the best interpolator for those type of oceanic surface data? The methodology that we use for this benchmark is called an OCE, which means observing simulating system experiment. As you can see on this diagram, we work initially with a fully complete spatio-temporal data field. We will see which one is just after. We kept part of this data set in order to realize data assimilation, learning with methods. And also, we take a smaller part of this data set, which will be used for testing and for validating the reconstruction. This data will be depreciated by adding a cloud mask. For this work, the cloud mask came from MODIS observation, which represent almost 18% of data available. So it's quite high rate of unavailable data. And we had also a Gaussian noise, which represents 30% of absolute error value on this data set. So we got here an illustration of our simulated observation, so with noise and cloud. Then we put this depreciated data in our construction models, so which can be some data simulation on our network. Then we got the reconstruct domain, the interpolation proposed by the model, and we use the true data set, this part, to validate and evaluating the quality of the reconstruction. Concerning the true data, the model that in which we made this work, it's a hydrosedimentary model, the Mars Mustang model from Baptiste Magal from Ufraber. We define a zone of interest in the Bay of Biscay, which represents a girl with 65 and 65 pixels. This hydrosedimentary model focusing on characterize the turbidity in surface and at the bottom of the sea. So it fits perfectly with our problematic. We got only 4 years of data available from 2008 to 2011. So the 3 first years will be used at learning and assimilation data, and then the last 100 days are considered to our testing data set and are depreciating. Considering the benchmark, we consider 5 methods. First, a classical optimal interpolation, then a DNF, the analog data assimilation, which some people here may know, and then 2 other architecture based on machine learning. First, an autoencoder neural network, and then another neural network based on Gibbs energy formulation. Concerning the 3 first methods, there are classical data assimilation method. The first optimal interpolation is just minimization of the variance estimator. As you can see here, we got our true state here, our observation term here. And we try to optimize the Kalman gain by working on covariance matrices. We got here the transition matrix H, sorry, to transform to the observation state to the true state space. Then we got the DNeoF. DNeoF is interpolator, iterative interpolator based on a OF decomposition. To be quick, OF decomposition focusing on a decomposition in time and space. Sorry, refer to the U and S and singular value F, V. Sorry. The user can choose the amount of component of the decomposition, which means more component it will have in the decomposition, and more the explained variance of the representation will be height. So the integration process is a projection reconstruction step using an OF basis, while observed variables are kept unchanged after each iteration. We only replace the missing data in each iteration in order to have the better reconstruction. Means that have the more closer to the full EOF field. Okay. The last data assimilation method used in this work is the analog data assimilation, ANDA, which combine an analog forecasting model to Kalman projection smoother to address the data-driven space-time interpolation of spatiotemporal dynamics. We see here for the state X, we got the A operator, which derive from the linear approximation of one-step ahead mapping belongs analog and successor for some reference dataset. In this graph here, we know the operator A through the way into a catalog of analog and successor, and in function of observation and previous dynamic, propose multiple solutions for the T+1 reconstruction, and the KMS pulsar with help to select the best one and the one who fits better with the situation. Concerning machine learning method, the interpolation is considered as a minimization issue. So as you can see here, we just try to minimize the relation between the state and the interpolator. So our interpolator here will, similarly to DNeoF, we may consider a fixed step iterative algorithm to solve the minimization for an operator, a phi operator given. The architecture will use irregular sample input here, and aims are trained to retrieving a gap-free field as output. The training phase here is stayed at the minimization of the reconstruction error. Please note also that we can work on the entire space domain, or we can also, as in DNeoF, focus only on the observed domain, which means only on the available data. So here we work on a fixed point projection iteration, which means that for each epoch of the operator, we try to optimize the minimization of the error by putting it in a non-parameterable fixed point projection, and then we start the learning with the new data projected. Yeah. But concerning the phi operator, we consider for this work two main architecture. The first one based on autoencoder formulation. As you can see here, we got the two classical parts of an autoencoder, the encoder and the decoder, with some classical convolution layer, and also the transpose for the true state. Just please note for the encoder formulation, which needs a lot of parameters for this case. We got like 500k parameters, and the other formulation, the Gibbs energy formulation, which are quite different because it uses ResNet is more which allow this method to be to have less parameter. We are around 80k parameters, so it's quite less than the autoencoder, and work on as I say, ResNet architecture with convolutional layer. Concerning the result of this benchmark, first concerning the global analysis, we note clear improvement of the neural network method concerning from theory in terms of RMSE, but also in R factor. Particularly the GNN formulation allow to have quite a great relative gain from theory. And as you can see here, the GNN formulation is quite more robust concerning period, which we don't have any observation. All red bar here indicate more than 90% of unavailable data for this period. For example, here it's clearly an improvement of the GNN, particularly the neural network method, and particularly GNN here. Okay, we got I've got a GIF here, so in PDF it not work, but it's not a problem. Secondly, concerning the specialization of the error and the specialization of the reconstruction for each method, I think it's really relevant with the gradient representation. Here you got the space norm gradient representation for each method and the true state, and you have here a map error for all the reconstruction. So first, the first thing what we see is that configuring the true data gradient, NN method, and also particularly GNN success to have the best dynamic representation, and it's clearly visible on the error map, which we don't have. Except artifact, we don't have a great zone of error located like in optimal interpolation, DNF, or and yeah, focusing on the RNG Gironde, estuary, we got a great representation of this gradient norm. Instead, in the sediment flux around Armoutier, we got an overestimation for the data assimilation method, and mainly the DNF and the OI. And in the presentation, we talk about interpolation, but also forecasting. Why we decide to work in provision? It's because when we're referring to the amount of data available in the data set on which we realize the interpolation benchmark, we notice that there are plenty of periods then we have more than 10 days missing, like here and there. And we are also more period with a 5 days of data missing. So we consider that if we can interpolate, reconstruct a fully spatial temporal domain with this method, with 10 days of absolutely no information, why can we try to do the same, but with prediction, basing of the hypothesis that we can work on the same methodology, considering that finally the prediction is just an interpolation without any observation. That's why we work on this following scheme. We consider the same learning dataset, and we construct 350 series of, 45 days each, with the first part of 30 days of observation and 15 days of blank field, which means that the interpolator has to reconstruct the data. As the first OSSE, we have the true dataset, which may be used in a validation way. We add another NN solver, which work we have some differences with the fixed point architecture, because the solver for this time is parametrable, because it's gradient descent optimized by LSTM. So the variational cost is quite modified. We got here the observational time, and here we have the same variational cost as the other NN method. So here you see that the main goal are the same. We put some depreciated input, and we want to have a fully reconstructed data fields in output. The same difference here is that during the learning of the model, each learning of the operator will be optimized by the minimization by the training by the trainable gradient dataset on this of this method. So actually, those predictions are work in progress. So the results that are shown here tends to be upgraded, but a first thing that we can see on this RMSE graph, which represent the mean RMSE for the five first day of each series of the 315. As you can see here, we got the 315 series, and each point refer to the 5 first day of the series. We got the red series here, which are the interpolating result for those series. So it may be our goal, our best reconstruction objective. So the first thing that we can notice is that the Cat-Devar reconstruction method give the best reconstruction, the best prediction for this 5 first day, but it's not perfect, because we see that with this purple line here, that all the data higher than this limit are considered as absolutely unusable, because they are they represent more than 50% absolute error. So this is not absolutely not useful for for analysis. But what are very relevant, very encouraging is again with the 2D norm gradient. Here we got the 2D norm gradient for the tree neural network method for the true state, which is very interesting. That the GNN method and the CatDeva and method succeed quite well to keep the again the Gironde estuary dynamics. And I think even if those gradients are underestimated for the moment, we may succeed to upgrade this reconstruction and have a better result and continue to ameliorate the reconstruction. So some prospection with this work. First, with the interpolation work, we want to test with real observation, real satellite observation, because at least we only work on a depreciated model data. So it may a good validation way for this work. Then again, continue the parameterization of the CatDeva model in order to have, as I say, a better estimation of the spatial gradient, which I think will significantly increase the result. Then we want to testing the stability of the model by varying the quantity of learning data available, which means that determine when the model succeed to have a correct reconstruction and know where we don't have enough data to do it. Then the next step is working on a multivariational learning in which we will add some features like oceanic forcing. I think of wave salinity, wind, maybe the SST. This kind of experiments have a great interest in terms of oceanic analysis, because it may help to understand which oceanic forcing have the more link, the more correlation between the sea surface sediment and the evolution of those dynamics. And then the last step of this prediction work is working on a way to bring a spatial and temporal uncertainty given by the model. Those sort of information about the reconstruction confidence may give a great upgrade of the project concerning the capacity of reproduce those experiments in other temporal situation, in other zone of interest. So I think one of the key points of this work to have a new prediction tool for surface oceanic analysis. So thanks for your attention. I'm waiting for your question. Thanks.
Thanks, Jean-Marie. Are there any questions or comments?
Hi, I do have one.
Go ahead.
Thank you, Jean-Marie, for presentation. If you just can go back to your last result slide on the results for the
Up. This one?
Yes. So if I'm not sure if I understood correctly, but your green curve is your 4D version with where you learn your optimizer, right?
Yep.
And the orange one is the same thing with a fixed point.
Yep.
So the only difference between the two is the fact that you learn the optimizer.
Yep.
Okay. Do you have any intuitions on why you have such a big gain in terms of performances, or impressive actually?
Yeah, it's quite impressive. And I think it's interesting that sometimes that the two different curves between learning optimizer and fixed point are quite the same in terms of RMSE patterns.
Yes, yeah.
But it just seems that is I don't have some intuition about that, but
maybe you are able to reach deeper certain local optima or something, because it's understandable. I think that you obtain the same error pattern. It will depend on the structure of your input data, maybe, or something like that. But
maybe.
Okay.
Maybe on this, I think we have quite the same kind of results for the application to SSH, where we have a significant improvement when we move from a fixed point solver to a gradient-based one. And I think I would expect this improvement to be greater here for forecasting, because you do not observe the future. So meaning that the fixed point is really just constraining one part of the state to be the observed data, and update with the projection according to the operator phi. And in the forecasting case, you just observe the past, and you have no observation for future. So you have very few constraints from data for the future. And I assume here that you optimize, Jean-Marie, directly the forecasting performance. You do not optimize the reconstruction of the past state, right?
Right.
Right.
Concerning just interpolation score between fixed point of CatDeva, we don't have a significantly gain between those two methods. For instance, the interpolation here is the best interpolation I have for the tree method is the GONN with a fixed point.
Okay, but maybe if you go back to the variational cost, which is considered.
Sorry. Yep.
Yeah. Basically, the idea is that, to me, when you consider the fixed point solver, you can consider you actually minimize this score to a construct X. But when you apply the trainable gradient solver, it's not clear whether you truly try to minimize this cost. And I think because you train the solver not only to based on the gradient of this, meaning that you probably minimize some of this cost, but the goal is truly to optimize your training loss, which is your forecasting performance. So I mean that the minimum of the variational cost may not be the optimum for the forecasting performance. And then the trainable solver would provide a better solution to use this variational cost and its gradient to optimize the training loss, which is the forecasting performance.
Okay.
I don't know if Said you follow me, but
I followed. Thank you for the intuition. It's maybe very obvious to use this at some point. Thank you, guys.